Well, good evening, everyone. Welcome to the February meeting of the North Jersey Astronomical Group. I'm Kevin Kanad, the president of the group, and so welcome, everyone. We're going to begin our meeting tonight with a presentation about the death of stars, and so really interesting topic. And so I'm going to ask Dr. Mary Lou West to do a little introduction here for our speaker. And so Mary Lou, if you could chime in.
Well, thank you, Kevin. So I'm a Cornellian and really enjoyed my time there some years ago, and provide a little bit of money to help a student, any undergraduate student who's studying astronomy in the summertime. And so the astronomy department chooses the student and the mentor of the student that will get my little stipend. And so this last summer, it was Anna Ho and her student Maggie Lee. And I was up at Cornell for my reunion, and I was able to meet them and have lunch with them. And it was great fun getting to talk to them. I thought it was so exciting to hear about the supernovas and the gamma ray bursts and other things that they would be researching in the summertime. And it came out very well in that there was a recent meeting of the American Astronomical Society in late January, and Maggie won one of the prizes as one of the best undergraduates. So I'm very proud of her. So I really think you do great work, and I was so happy that Anna agreed to give a talk to us tonight.
Oh, that's very kind of you. Thank you, Mary Lou, and good evening, everyone. Thank you for the invitation to join you all and speak here virtually this evening. As you've heard, my name is Anna Ho. I'm an assistant professor in Cornell's astronomy department, and I do research on the lives and deaths of stars, as well as on what I think of as the afterlives of their corpses. So for my research, we were just chatting about telescopes. So I use telescopes that are located in deserts and on mountaintops all over the Earth, as well as on satellites that are in low Earth orbit. And I use these telescopes to study how a star's properties in its life determine its manner of death and the type of corpse that it forms. So for example, whether that corpse is a neutron star, a magnetar, or a black hole. And a unifying theme in my research using these telescopes is the observation and interpretation of change. So that is that the signals that I collect from these stars and their corpses change very quickly on timescales that we can perceive. And most of these signals can't be seen by the human eye. So I thought what I would do this evening is give you an introduction to this sort of dynamic and many times invisible universe, and talk about what it can teach us and how we as astronomers can reveal it. And I'm not sure how this usually goes, but I'm quite happy for this to be sort of a conversation. So please don't hesitate to interrupt me at any point if you have questions. And if I don't know the answer right away, feel free to contact me via email, and I'd be happy to follow up later on. So before I launch into stellar death, I thought I would just orient you by talking about what the night sky looks like to our eyes. So the human eye, as you know, is an incredibly powerful detector. We can see a huge range of brightnesses. So the faintest light we can see is about 10 billion times fainter than the brightest light we can see. Our eye takes a picture and sort of sends that picture to our brain about 15 times per second. And that very rapid frame rate or imaging rate enables us to notice very fast changes in our surroundings and to react quickly. And then, of course, we can also see a very wide range of colors. So when you use your eye, this detector, to look at a dark night sky, you see something like this. So almost every single dot that you see is a star inside of our galaxy, the Milky Way. And if it's really dark, you can see a band of fuzzy white material. That's actually just a lot of stars, so many in a small area that our eyes can't resolve them into individual dots. And then in some areas, these stars are blocked by what look like dark bands. And these are clouds in a way, but clouds of gas and dust that lie between the stars in our galaxy. And there are only a few objects located outside the Milky Way that we can see with our eyes. There is the Andromeda galaxy, which is the closest big galaxy to our own. And then there are the LMC and the SMC, which are small satellite galaxies orbiting the Milky Way. And if you look, so you look at the sky every night, for the most part, it'll look the same, but you might see some changes. The position of the moon will change, the position of the planets will change, see a shooting star, a meteor, a comet. And if you're very lucky, about once per century, you'll see something very dramatic. So this is an image of the Milky Way's larger satellite galaxy, the LMC. This is an image of it before the special date, 24th February, 1987. And this is an image of it shortly afterwards. And does anyone see a difference from one image to the other? All right, I'll reveal where it is. Can you see that right there?
Yes.
Oh, yeah.
So
Oh,
there
yeah.
is a new star visible to the naked eye, although these particular images were taken with a camera. So now we'll zoom in to that spot using a telescope. So a telescope offers several major advantages to our eye. It's bigger, so you can collect more light and see things that are fainter. But also very important is you get much better resolution. So you can see individual stars in a region that would just look like a blur to our eyes. So on the left here is a telescope image of that position before that date. There's a star at this location, this minus 69 degrees 202 right here. And it's a star of a type called a blue supergiant, which basically means that it's a star that's fairly advanced in its age. And then afterwards, that star was confirmed to have disappeared. And in its place was something 200 million times brighter. So you can probably guess what that was. And that was a supernova. So this is by far the best studied supernova ever, still, because it happened so close to Earth at a time when we had telescopes to study it. And we learned a lot about stellar life and death from this event. So I think it's a really great introduction to stellar death. And I'll now tell you a little bit more about it. So first, a very brief overview of this topic. So we think that stars form when a cloud of gas and dust collapses and heats up. If the star is similar to the sun in terms of how much it weighs, so we say a sun-like star, it lives for billions of years, becomes a red giant. This star lives by burning fuel, so it fuses hydrogen to helium, but eventually it runs out of hydrogen to burn. When that happens, its outer part, its envelope, sort of blows off and becomes a planetary nebula, and that exposes the core of the star, which is very hot because it was way inside of the star. Typically by this point, it's made just of carbon and oxygen, and we call this remnant or the corpse a white dwarf. Now, if, on the other hand, the star is very massive, so it weighs more than around 8 to 10 times the mass of the sun, it goes through its life much more quickly. So whereas I mentioned a star like the sun will live for billions of years, a massive star will only live for millions of years before it becomes a red supergiant. And when it runs out of fuel to burn, it explodes as a supernova, and the inner parts collapse and form a neutron star. And if this neutron star is massive enough, it collapses further and becomes a black hole. These supernovae are really remarkable celestial events. In the first 10 seconds, a region 20 miles across radiates more energy than all the stars and galaxies in the rest of the visible universe combined. And that sounds kind of scary, but it's actually quite wonderful because these events are the origin of the elements that we need for life. So carbon, iron, oxygen, nitrogen, and others that I'll show you in a bit. So these elements.
Gold.
Oh, yes, please.
I was just saying gold.
Oh, well, right. So gold. So in the last few years, we've been able to study not just supernovae, so not the depths of stars, but actually the mergers of neutron stars. So after two stars have gone supernova, you have two neutron stars, they can merge again and make another explosion. And that has been shown to be the source of a lot of gold. So you can to synthesize these things, you basically need high temperatures. And you can get high temperatures in various different conditions, but you also need certain compositions of certain elements. So you won't make everything in the same kind of event. So yeah, we think, supernovae themselves, we think, are the dominant production channel for a bunch of elements, including the ones I'm listing here. They can be made inside the star during its life and then shared with the universe during the supernova. Or actually, some of them can be forged during the explosion itself, because that's when matter gets heated to even higher temperatures. And that's kind of what we think is happening with the gold. It's formed in the collision in that actual event. So that's what I would describe as the textbook story of stellar life and death. It's what we teach students, what I taught students last semester in introductory astronomy classes. And in many ways, supernova 1987A was an amazing vindication of important elements of this textbook story. It was really the first time in a lot of ways that the story was tested observationally, but it also brought some big surprises. So surprise number one, this was the first time that a star was detected and then the subsequent supernova. So it was sort of, confirmation that stars do actually explode, but it was actually the wrong kind of star. So astronomers had expected a red supergiant. This star was a blue supergiant. And this forced a revision of the story. And just kind of long story short, you have to take into account not just the mass of the star, but also the composition of the gas, so the raw material that the star is made of. And today we know that that's an essential part of the story. So just to tell you a little bit more about the star, astronomers think it was around 18 times the mass of the sun and lived for around 10 million years. And actually something interesting that I'll mention now and then return to later is that this star spent pretty much all of those 10 million years burning through its hydrogen. And then it spent 1 million years burning through its helium. Then it spent about 12,000 years to finish its carbon, then 12 years to burn neon, 4 years to burn oxygen, and a week to burn silicon. And that's the end. So once you burn silicon to iron, you're done. You can't burn iron. So those final stages actually happen really quickly on human timescales. And that gives you a hint already about why it might be that we might see things happening even over the course of our lifetimes. All right, but anyway, I'm getting kind of ahead of myself. So another major landmark from this supernova was the detection of mysterious particles called neutrinos. Neutrinos are tiny particles. You've probably heard of electrons, tiny electrically charged particles. Neutrinos are called neutrinos because they're neutral, so they have no electric charge, and they're way tinier than even electrons. And because they have very little mass and have no charge, it's really hard to get them to interact with anything. So the Earth is actually much more, the Earth is much more transparent to neutrinos than a sheet of glass is to light. But there are dedicated experiments under the Earth that can detect neutrinos. Basically, you construct a giant tank of water and detect the tiny signal from a neutrino interacting with a proton in the water. And until this point, neutrinos had only ever been detected from the sun. But they had been predicted theoretically to be the first signal to leave a supernova. And indeed, they were the first signal to be detected from supernova 1987A. So 3 different detectors in very different places on Earth detected these neutrinos washing over the Earth, which I think is quite amazing. And even more amazing is that the amount of energy amount of energy contained in these neutrinos is exactly the amount of energy that you expect a star to release when it collapses and forms a neutron star, with exactly the predicted mass of the neutron star, the predicted temperature. So this is an amazing vindication of the theory that stars collapse and form neutron stars. We actually also learned a lot about the physics of neutrinos themselves, which I won't get into. But one puzzle actually is that even today, we have still not seen this neutron star. So people are still actively searching for it. There are some, every now and then there's a paper saying, oh, we think we see the neutron star. And then people say, well, that could be something else, blah, blah, blah. So whenever there's really definitive evidence of that, that's going to be big news in the field. So we're still kind of waiting for it to show up. So just to be clear, it's there, it should be there. It's just that there's a lot of stuff lying around. And so it just takes a while for that stuff to become sort of diffuse enough for us to see through it and see that neutron star. Okay, so that's the corpse. Astronomers also got amazing spectroscopic observations. So this is a spectrum of the infrared part of the electromagnetic spectrum. So different elements give rise to different peaks or features in the spectrum. And you can read a spectrum like a fingerprint to identify which elements are involved. And so this is just an incomplete list of the ones that were found in 1987A. And again, just a really nice demonstration of what we expected, which is that these kinds of elements should be synthesized in stars and in supernovae. Okay, there's just one more thing I want to mention about 1987A, and that is that its structure was extremely complex. So this is an image taken with the Hubble Space Telescope of the field. So zooming in, it had these rings. So this is kind of, we're looking at it kind of from an angle. So there's this kind of inner ring, which is bright, and then these two other rings that are stacked one on top of the other, kind of like an hourglass. And over time, astronomers have been able to watch these rings change. So this is time-lapse footage. So from 1994, we're going forward many years. And you can see that over time, this ring, this is the inner ring, is actually brightening over a decade. People have been monitoring this for quite a long time. So what is going on here? So we think that this ring was actually formed 30,000 years before the star exploded. So when the star exploded, it was surrounded by these complicated structures. So it's a kind of record of the final stages of the star's existence. And then the light from the supernova, the shock wave launched by the explosion, sort of crashed into this ring after the explosion and heated up the gas in the ring, which then caused it to light up. And so why would a star have rings surrounding it when it exploded? This is evidence that stars do very complicated things shortly prior to their deaths. And today we understand that these things I like to call death omens are one of the most important predictors, actually, of how the star will ultimately die, and also what kind of corpse it will leave behind.
Are you saying, I'm sorry to interrupt, but it took
Yeah.
almost 30 years for the explosion to light up the ring?
That's right. Yep. So just from the speed of the ejecta, that's how long it took to reach that distance. Yep.
Impressive.
Yeah. Yes, indeed. Right. So just to
Excuse me,
kind of,
Anna,
oh yes, please.
how large do they estimate the ring to be?
That's a good question. I mean, we can sort of, I guess, I don't know. Oh no, here, 1 light year
Oh,
across.
well, okay, much larger than I thought. Okay.
Yeah,
Thank
so that's about right, because then it took 30 years, which makes sense because the ejecta is not going to move faster than the speed of light. So yeah.
And Anna, could you explain the other two rings a little bit more?
Yeah, so we don't really know how all these rings formed. It's actually, yeah, that's a big open question in this field, is what is the mechanism? So what we definitely know from this object and also a lot of subsequent observations is that in the final kind of days to centuries before they explode, after shining for millions of years, stars can become kind of unstable in some way, and they can actually shed a significant fraction of their mass into their environment. Why they do this, what is the physical mechanism that causes them to do this, is actually not known. The fact that it's a ring tells you that it's not a spherical process. So it's not something where the star, it's not like a wind where it's just sort of blowing in all directions equally. So one way you can get a ring-like structure is if the star had some kind of binary companion, then this companion can strip material off the star, and that will happen preferentially in kind of a plane. And maybe that helps you get a ring. So if it happens and then stops, then the thing will kind of just, you could get a sort of ring with a gap if that process ended. So that is one theory for how you can get these structures, but that's actually a major topic of research nowadays.
And there's
It's actually a little
one.
bit. Oh yeah, sorry.
I'm sorry, I was going to say there's an additional ring sort of above it and one below it.
That's right.
Just interesting. Yeah.
Yeah, it's amazing. And we don't get this data for the vast majority of supernovae because most of them are way too far away, but we infer the presence of such structures from the emission that we detect. So you can kind of infer that they're there, but you can't actually figure out what their geometry is. So this is one of the few cases where we actually have the geometry, and it's still not really known where it comes from. So,
And we're confident they're not three-dimensional structures, like, even though, in other words, they're not spherical, because we can't we can't look at a different angle, right? It's
that's
not
true.
just thin enough at the angle we're looking at in that direction that we can't appreciate it. Does that make sense?
So I think I know. So you're saying, how can you unproject this into 3D?
Well, there could be a ring that's straight on that we're looking at. We just don't appreciate it because there's so much other light and things going on.
I see. Yeah. So, right. So there's what you can actually see visually kind of comes from the interaction. So so there was all this structure was here. Then there was an explosion of quite a significant amount of matter was expelled at enormous near speed of light speeds. That stuff crashes into the material around it and lights it up eventually. So it's true, there could be something much further out that's so faint we can't see it. But what we have extensive observations of the interaction over now several decades. So we have pretty good tomography, basically, of the material out to a certain distance. And another thing, this is optical light that we're looking at, but interaction actually also produces emission in the radio band, in the X-ray band, and these different bands are sensitive to material that has different densities. So we actually have a pretty complete view, I think, of the structure of this stuff, at least out to the distance that the ejecta has reached, because we're not just seeing it visually, we're actually seeing the interaction in multiple bands of the electromagnetic spectrum. But yeah, there are limits. You have to make some assumptions to then figure out the geometry if it's not something you're actually visually seeing. But I think it's probably fair to say that we have a pretty complete picture of how much stuff there is, at least out to the distance the shock has reached.
Got it.
Okay, so maybe I'll just move on here in the interest of time, just to wrap up this section. So just to kind of put all this together into something called a light curve, because I'm going to show some light curves later, so I want you to know what I mean. So a light curve is just the amount of light you're detecting over time. So on the x-axis here, the horizontal axis, you show time in days. So this is 0 days, that means the time of explosion. This is about a year later. And then on the vertical axis here, we have the brightness. And so here we're 50 million times the brightness of the sun, 200 million times the brightness of the sun. And so you can see that at 0, there was this massive spike. This is in neutrinos. I mentioned the neutrinos. That carries actually most of the energy. Then they're done after just a few seconds. Then you come back down and then you start brightening again. And now the most of the light is coming out in the optical part of the electromagnetic spectrum. So the kind of light we can see with our eyes peaks at around, a couple months and then starts to fade away again. And there's a lot of really interesting physics in these light curves. The fade rate, actually all this emission is powered by radioactive decay. So there are elements synthesized in the explosion, sort of certain radioactive unstable isotopes. The most common one, at least early on, is nickel-56. Nickel-56 has a half-life of around 7 days. And that sort of dictates sort of some of the time scales here, and then that's done, and then you get cobalt-56, and that sort of takes you down the rest of the light curve. So the optical emission is primarily coming from photons emitted when isotopes are radioactively decaying, which is quite cool. So yeah, typical times, this is a fairly standard supernova. Time scales to go up and down are kind of months. So remember that, because later I'm going to show you that today we're discovering things where the time scales are minutes. So which is kind of the frontier. Okay, so just to wrap up this section, lessons learned, like I told you, we detected what we call the progenitor star. So saw it was a blue supergiant, not a red supergiant. Neutrinos were detected, which was evidence of neutron star formation. We saw evidence that supernovae and massive stars synthesize elements. We see that there's very complex structures in these stars. These are not spherical processes like what we teach in class, and we don't really know why, actually. I mean, what all this tells us is that this textbook story we have is very incomplete, and we have to take into account the composition of the gas the star is made of, what it did before it exploded, and that might have to do with its interaction with other stars, which quickly gets actually very complicated. All right, so that's all I wanted to say about supernova 1987A. I'll now move on to talking about what supernova discovery is like today, because we're not seeing things with our eyes for the most part. And I always like to talk about this in terms of advances in detector technology, And I'll talk about this with a telescope that I used for my PhD thesis and that I still use today. We were just talking about this before 8 o'clock. This is Palomar Observatory in Southern California. This telescope was built, 40-inch telescope was built, I think its construction finished in 1948. And then it spent 10 years doing a survey of the sky. So taking many images to sort of make a big mosaic. And it had a photographic plate. Today, that telescope is still active, but so the telescope itself has not changed. What has changed is that it's fully roboticized. So no person has to go and move it around. It just automatically goes and makes its mosaics. And the detector has changed. So instead of a photographic plate, there's a giant CCD camera. Things are now moving in the field to CMOS detectors, but this is a CCD camera. And with those changes, this same telescope can repeat that same 10-year survey in just a single night. So that's how much things have changed. And it's, I think, wonderful that it's the same telescope that's able to do this. So this is 1/64th of a real image taken with this telescope. It's a negative image, so all the little dots here are stars and galaxies, all kinds of things, asteroids probably. The full field of view is 47 square degrees, which is huge for at least these kinds of facilities. And I just like to have this guide in case you don't know how big that is. So that's about 7 by 7. So if you hold out, 3 of your fingers, it's sort of roughly that on each side of the square. And as far as telescopes go doing this kind of science, that's pretty much as big as it gets at this point. And there are a bunch of telescopes doing this, located all over the world. This telescope I was just describing, ZTF, is just one of them. There's also a facility called Assassin that has multiple telescopes in different places. The Atlas survey, which I think they have one telescope in Hawaii and then maybe a second one somewhere, and I can't remember immediately where. And just roughly the way this works, it's all fully automated now. No person is going to look at this image and look for the supernovae. That's not practical. And so it's fully automated. So you'll take each night, these telescopes take many, many new images. For each image, you subtract what's called a reference image. That's an image of what the sky kind of normally looks like in that location. And then you look for supernovae that way. And you define some critical threshold of significance. So if you know what this means, it'd be a 5 sigma detection and above counts as a new candidate supernova. And we typically call that an alert. So this is all done with machine learning now. So machine learning algorithm will take a look at this detection and give it a score. So how likely is it to be a real supernova versus just an artifact of bad subtraction? Because this is actually a very challenging problem, because the night sky, the conditions are changing all the time. So you can get changes that have nothing to do with having a supernova. So yeah, there's a basically machine learning model that makes a decision, helps us decide whether something is real or not. And then these so-called alerts is basically a packet of code that contains information about the source. So what is its right ascension? What is its declination? How bright is it? What are the history of detections at this source location? Is it near a known star in a catalog? Is it near a known galaxy? What's the redshift of the galaxy? And so on. So it's just sort of contextual information about the thing. And then you have to distribute this message to the whole worldwide astronomical community. And there are a bunch of things you need. You need the message to be reliably distributed. You need downstream listeners to be able to rewind through it. So say what alerts were found last night. You need a format that sort of preserves the integrity of the data so that it can be interpreted in a consistent way by the user. And so with all these requirements for ZTF, we're using a structured data format called Avro, which is JSON based. And it can handle an enormous number of alerts. And this is actually used by LinkedIn for their activity stream data. It powers the LinkedIn newsfeed. It's also used by companies like Twitter and Netflix. So this is very kind of industrial scale news streams that we're dealing with now from telescopes. All right, so to give you a sense for the scale, per night, this generates a few terabytes or so of data. And I'll just walk you through kind of what the numbers were just last night, because ZTF is observing every night. So last night, ZTF generated about 200,000 alerts. That is actually not even half of what we get on a really good night. On a really good night, it's about 500,000 alerts. Those come from about 170,000 unique sources. So you can go and group them basically by position. Of those, I would estimate that around 100,000 are sort of real. So we're actually dominated by kind of artifacts and all kinds of other things. Then a common cut that we apply is to require that each source has 2 or more detections that are separated by at least 30 minutes, because otherwise you get flooded with asteroids. So you get things that are actually moving across your image. You don't want something that's moving, you want something that's staying at the same position and changing. Then zooming in on those, I'm not looking for stars in our galaxy, I'm looking for supernovae outside our galaxy. So I typically remove everything that is known to be at the position of a star in the Milky Way. We have lots of catalogs nowadays. And then I focus my attention on things that are truly new. So something that was detected for the first time last night and had never been seen before in the history of anything, as far as we know. And that's how we find new supernovae. So the main message here, maybe if you learn one thing from my talk today, it's that it is no longer a big deal to find supernovae at all. So a new supernova is discovered every night. And the number in the universe is about 1 supernova every second. So we're still far from finding all the supernovae, but the state of the art today is about 1 per night. And this is a video.
Nice clear image.
Can you see it again?
Yes, now you're back on your screen.
Okay, good. Okay, for some reason, I think I can't show this video, but in any case, what this is showing, it would show a time-lapse video of all the supernovae that have been discovered over the past few years. And it builds up to thousands, very quickly, because it's about 1 per night. They're color-coded by the type of supernova. So one of the most common types are type 1a supernovae, which are exploding white dwarfs. There are core collapse supernovae, which are the kinds I've been talking about, collapsing massive stars, a weird, mysterious class called superluminous supernovae that can be 100 times brighter than regular supernovae, and nobody knows why. And this is just their locations in the sky of where they were discovered. A few things to notice. We don't find a lot of supernovae in the galactic plane, so in the plane of the Milky Way. That's just because they get shrouded. There's too much dust there. It basically blocks our ability to see things on the other side of it. And then there's this big gap here, because that's the Earth. So ZTF can't look through the Earth. So we don't see the south. We just see the northern sky. So it really is, it's a real kind of machine for discovering supernovae. And that's really changed the kind of science that we can do, because it's no longer sort of each individual supernova being studied by itself. It's really being able to study supernovae as a population. So doing kind of more like a census. All right, so it's actually still extremely rare to be able to look at the progenitors of supernovae. This is kind of a whole thing people try to do. Every time that there's a supernova in a nearby galaxy, people go and they try to see, oh, can we see the star that was there beforehand? So at this point, even though we found thousands and thousands of supernovae, there are only 17 that were close enough and had the kind of pre-explosion imaging that you'd need to detect the progenitor. And that includes 1987A. But at this point, we have confirmed that red supergiants do indeed make core collapse supernovae, as was theoretically expected. Okay, so that's how supernovae are actually discovered today. And now I want to talk a little bit about the state of the art in studying their corpses. So just to kind of reorient you, there are 2 kinds of corpses you can make. These are being formed in the deaths. I'm going to focus on the ones formed in the deaths of massive stars and not the white dwarfs. The supernova, the ones that are kind of more massive, ultimately form a black hole, and the ones that are a little less massive, so less than 20 times or so the mass of the sun, end up forming neutron stars. And so first I'll say a bit about the neutron stars. These are quite small, actually. So their size is around the size of a city like Manhattan, but they're heavy. So they weigh 1.5 times the mass of the sun. So these are incredibly dense objects. They're about as dense as you can get. If you get any denser, you collapse and you form a black hole. So this is kind of the limit of what matter can do. And they're so dense that the escape velocity, so if you're on the surface of a neutron star, to get off, you have to travel at 0.7 times the speed of light. So you have to get up close to the speed of light. So that's a sort of one way to think about how incredibly dense they are. They have an incredibly powerful gravitational pull. And so at this point, about 3,000 neutron stars are known. The vast majority are discovered in the Milky Way and are discovered as pulsars. So what is a pulsar? I like to introduce them through their discovery. So they were discovered by Jocelyn Bell, who was a PhD student at Cambridge University in 1967. She was there to do radio astronomy. So her first job was to build an enormous radio telescope. So she and 4 other people strung up 2,000 radio antennas covering more than, I think they were connected by more than 120 miles of wire and cable on a field big enough to fit 57 tennis courts. So it took them 2 years, and it was her job to analyze the data. So today, when I do research, the data is stored on my computer. I can analyze it by programming, basically. But her radio telescope spat out 100 feet of chart paper every day, sort of like a seismograph, a pen and chart recorder. And she would analyze this data by hand. And while analyzing it, she noticed something very strange, this sequence of little pulses spaced exactly 1 1/3 seconds apart. And she realized that as she watched these pulses from day to day, based on the way that they shifted from day to day, they had to be coming from outer space. They couldn't be coming from the Earth. And so this was a dramatic new discovery. And as you can probably guess, these are pulsars. So these objects are named, they're short for pulsating star, even though they're actually not really stars. Here is a really famous one. This is the Crab pulsar, where we think humans saw the supernova that's represented in cave painting in Chaco Canyon, New Mexico. And this is recent optical imaging of the Crab pulsar. So you can probably see there, you can actually see it in the optical band as well. So it does radio pulsations, but it also makes optical pulsations through a different physical process. And that's a real-time video. So with a special kind of high-speed camera mounted on a different telescope, actually at Palomar Observatory. So the pulsar is a nice example where you can see the pulsar, you can see there's a stellar corpse. It's embedded inside of this supernova remnant. So so the thing exploded, it left behind a neutron star or a pulsar, and then all that ejecta, that stuff, formed this really beautiful nebula. Right, so those are pulsars, neutron stars. This is an artist rendition of how we think they work. They have really powerful magnetic fields in this kind of dipole arrangement, kind of like what the Earth has. And so you have a north magnetic pole, a south magnetic pole, and then as you spin around, electrons accelerate along these magnetic field lines, and they produce, an accelerating particle produces radiation. And just the way the geometry is, you get a beam of radiation out one pole and a beam of radiation out the other pole. And then as it spins around, these things whip by Earth, kind of like a lighthouse. And so that's the origin of this pulsed emission. Right, so at this point, we have thousands of pulsars. And actually, I have a very special place in my heart for pulsars because this is the subject of my very first research project in astronomy when I was an undergraduate summer student. And it really was part of what sparked my excitement about being an astronomer. And I got to go to the telescope that we were using to discover new pulsars. So the Green Bank Telescope in West Virginia. So it's the largest steerable object on land, actually. You have to take an elevator to get to the top. It's 100 meters across. Okay, so that's neutron stars. A little bit about black holes. Like I said, if a neutron star accretes any more material, it will no longer be able to sustain itself as regular matter. It will collapse, form a black hole. You've probably heard that these are so dense that nothing can escape, not even light. They don't even emit or reflect light. But we can still actually see them in a way. And actually, a lot of my research is studying the influence of black holes. Because even though you can't see anything that comes from the black hole, kind of counterintuitively, they are still the engines of the brightest radiation sources in the universe. And the reason for that is that they have the strongest gravity of any other source in the universe. And so the gravity is so strong that it can really warp the material around it. So if there's any stuff anywhere near this black hole, it's going to get accreted. So this is a companion. This is an artist rendition of a real known source. It's called an X-ray binary, which it's not that important, but it's a binary system. So there's a black hole, there's a surviving star, it accretes that material, and the gravitational pull is so powerful that all of this stuff gets really, really hot. There's a lot of friction, and it can tap into the energy, the gravitational energy of that black hole, and power jets. So material gets funneled kind of up and below. And some of these things, versions of this we see from supernovae actually, from the newborn black holes in supernovae. And these are the brightest known radiation sources in the entire universe. So it's really quite amazing.
Question?
Yes, please.
Can we see a neutron star? Are they just too
So-
small?
Right. So they are very, very, they on their own are very, very faint. So it's sort of, you'd have to be very nearby to actually just see it. So almost all the time, what we're seeing is their sort of influence via their beams as a pulsar or pulsations from things kind of falling onto them and heating up, kind of like the black hole. So we see their influence a lot more than we really see them.
Okay.
That said, there's another way we can see neutron stars and black holes nowadays, and that's gravitational waves. So these very dense sources, they also warp the space-time around them. And that warp basically can actually propagate all the way to the Earth and distort everything, all matter on the Earth. It's only distorted by a very tiny amount, so don't worry, but it's actually detectable nowadays, which is an absolutely amazing technical feat. And this is just an animation. A numerical relativity group actually at Cornell made these simulations of kind of what you expect these things to look like. And today, these gravitational wave detectors routinely detect the mergers of black holes, also the mergers of neutron stars, and also the mergers of black holes and neutron stars. So it's not seeing exactly, but it is another way to perceive them. It's just a completely new way. So it's not seeing, it's not hearing, it's just a different kind of perception.
And that was a simulation?
That was a simulation, yeah.
Okay.
Yep. All
Thank
right.
you.
Yes. Right. So that's, we've talked now about sort of regular supernovae, how we study the corpses of these systems. And now in the last part, I want to talk about some of these extreme kinds of supernovae. And so the point is that once you start discovering a lot of different supernovae, you start finding ones that don't behave as you expect. And these have been the focus of my research in the last couple of years. And you might ask, why study the outliers? And the answer is that we make enormous progress from finding the cases that break our models, because often they are sort of expose our ignorance about important aspects of these models. And so actually counterintuitively, these odd cases can actually help us make a lot of progress in understanding very widespread behavior. So I'll show you a few examples. So I like to summarize sort of how we find these extreme systems with this diagram. So this is very similar to the light curve that I already showed you. So on the horizontal axis here, I'm going to plot the duration of the supernova. And I've already told you that for most supernovae, it's kind of more like months. That's set by fundamental physics, radioactive decay. And on the vertical axis, I'm going to show you the peak brightness. So how bright the supernova get at peak. And for normal supernovae, there's kind of a relationship that you can derive based on radioactive decay. They're basically all here. So the brighter you are, the longer you'll go. And also the fainter you are, you can go shorter. And so 1987A is very much safely within the kind of normal supernova regime. And it should be impossible for something to be outside of it if it's the same, if it has kind of the same powering mechanism as a regular supernova. What my group, including Maggie, has been doing in the last few years is discovering things that are not in that region. So here they all are. So now I've filled in this bottom right region with dots. So these are just real supernovae discovered by ZTF, white dwarf explosions, core collapse explosions. And we have all these things that we've discovered that are much faster and much brighter. And fortunately, I'm just not going to have time to kind of go into each of them and say what they are. They all have, these are called orphan afterglows. These are related to gamma ray bursts. And these things called luminous fast blue optical transients. And their flares, which can be just a few minutes. Something else that's powered by what's called a kind of shock breakout from the surface of the star. So yeah, I'll talk about some of these now just briefly, but unfortunately, won't be able to really do this all justice. But just to say that with facilities like ZTF, now that we're actually coming and scanning the sky, we scan big parts of the sky, not just once per night, but multiple times per night. And that's how we're able to discover these things that are much faster. So when you look at the sky in a new way, you always discover things that you really weren't expecting to see. And that is a really exciting part of research. Okay, so I'll say just a few words about these fast glow optical transients. So what are they? So these are not kind of regular supernovae, but we think they are kind of associated with supernovae. But the signal that we're seeing is not dominated by the canonical radioactive decay part of the supernova. That is actually sort of subsumed by a much brighter signal. And that's the signal from the collision of the explosion with the ambient material. So I mentioned that in 1987A, we saw that ring light up. But this is a much more extreme case where that ring is a lot denser and a lot closer. And that means that it becomes a lot brighter. And it's actually so bright that it outshines the supernova. And that's the really fast signal we think that we see. So these are kind of laboratories for us to study this end-of-life mass loss that stars can undergo. And at this point, we think that about 1 in 100 stars explode surrounded by very dense gas, meaning that they did something before they exploded. So what did they do? So this is something I mentioned for 1987A. One clue as to what they might be doing is the duration of these different nuclear burning stages. So I mentioned that you burn hydrogen to helium, that can take millions of years. But by the time you get to the last stages, burning your oxygen, burning your silicon, these are actually very short timescales. And the core collapse event is very, very quick. And so one theory, so I mentioned one theory is that you can lose mass from a companion interaction, but another theory is that you can lose mass because of changes occurring deep in the interior of the star. So each of these stages is much, much more sort of energetic than the previous stage. So by the time you're burning silicon to iron, your temperatures are way, way up. Your luminosities, the amount of energy that you're producing is way, way, way up. And there's a theory that actually that those numbers get so high that you excite sort of waves that can actually propagate to the surface of the star and push off mass. So it could be that the mass that is lost is actually originating in changes that are happening inside the core of the star. And it was never thought before that that's physically possible because it wasn't thought that you could transmit information from the core of the star to the outside. But this could be evidence that this actually can happen and that there are sort of new energy transport mechanisms inside of stars that can get that information out about which kinds of elements you are burning. So that's a theory. It's being tested observationally. But if true, that would be really beautiful.
And I have another question.
Yes, please, go ahead.
Don't beat me up.
No.
The core collapse, is that literally just the core that's collapsing in on of itself? Or is it the gas that surrounds the core that's descending upon the core?
Right. Very good question. It is actually the core that's collapsing. So what causes it is that the core, over time, so in the core, it's made of different, so at the beginning, the whole core is made of hydrogen, then it burns that hydrogen to helium, then it runs out, then it starts burning that helium. So it sort of goes through all these elements. Eventually you get to the point where the whole core is made of iron. So you've converted all your silicon to iron. Iron has this very special property that it actually takes energy to burn your iron rather than releases energy. So you switch, you actually can't continue basically. You run out of steam. So once you have iron, you're done. And then what happens is that because you don't have, so you can't sort of continue, you have no source of energy, which means you have no source of pressure. And so gravity now can just kind of take over. And there are other more complicated things that can happen, but basically all your atoms there, they kind of dissociate and just the whole thing just falls apart very quickly. So the core actually itself collapses. And the innermost parts kind of collapse first because they're the highest densities, highest temperatures, and so on. And then then once that happens, if you're a shell sitting on top of the core, everything beneath you, the floor has literally fallen away from you, you will fall as well. And this is supersonic, like it's really, it's just very, very fast. And then everything starts kind of caving in. But then what happens is that, so things fall in, the outermost parts still have no idea because they have not received the message that the floor is gone. But what happens is that implosion, there's kind of a rebound because it's so dense that you can't just kind of collapse and just keep going. Eventually you collapse so much that you rebound, and the rebound basically ejects material, and that explodes the outer layers of the star.
Ah, okay.
Yeah. And it doesn't actually work. So a long-standing problem in the field was to try to get this process to work in simulations. And for probably decades, it just didn't work. Stars just wouldn't explode in simulations. And actually, I went to a conference this year where basically the major report was, okay, now they all explode. And the reason why they all explode now is it turns out you need to simulate it in 3 dimensions. You can't do it in 2 dimensions. They were being represented in 2 dimensions because that's computationally more tractable. But you need 3 dimensions because it turns out that actually to get this process to work, you need turbulence and things that only really exist in 3 dimensions. So yeah, that was a big puzzle in the field for a long time. Okay, I'm going to actually skip to this last topic here, just in the interest of time, which is for these sort of F-bots that I was talking about, a really strange mystery that we discovered just last year. So the whole story with these F-bots was that the very first one was discovered in 2018. And when you discover these explosions, they get a name, astronomical transient, and then the year of discovery, and then a string of letters corresponding to just the first one will be A, and then it's B, then it's C, and then AA, AB, AC, and so on. So this first one was actually coincidentally called 2018 COW, or the cow. And it attracted a lot of attention because it had really special properties. It was very different from normal supernovae. There were all kinds of theories about what this could be. Oh, maybe it's a case where the supernova didn't actually explode and it collapsed in on itself. Maybe it was actually not a supernova. It was the merger of a star with a black hole, something like that. So since 2018, my group and I have been trying to understand the origin of some of these events. And so we have been collecting new data on new ones that we discover using ZTF. And basically 1 year ago now, or a little over a year ago, December 2022, we had this amazing observation. And so these are the images. Okay, so this is 100 days after the original explosion. So there's some explosion we didn't know. We don't actually know what happened or what exactly it was. 100 days later, we expected it to just be fading away, and it was kind of fading away. So we were just getting images kind of routinely to see how quickly does it fade away. Then we got this sequence of 5 images. Each image, the exposure was 3 minutes. So this is a 15-minute sequence. And this is the galaxy that the original explosion was in. And what you can see is that over the course of 15 minutes, something was not there, which is what we expected. Then there was something there, then it got really bright, and then it faded away again by the end. So in the aftermath of something else, which was also mysterious, there was something that lasted less than 15 minutes. And the peak brightness of this thing was actually as bright as the original explosion. So the power, it was as powerful as the original explosion. And we have no idea what it was. So maybe I'll leave it at that with a mystery of minutes duration supernova-like transients, and take any questions that you have in the last few minutes here.
Hi.
Is this one invisible light or infrared?
This is visible light, yes.
And would it be all right to ask a question, maybe slightly a little off topic, but certainly part of moving the discoveries forward?
Yeah.
Oh, great. And I have to apologize if Mary Lou already mentioned this earlier. I had a little trouble with my network, so I missed the beginning. Is there any update on Ultrasat? I believe that's a project you're involved in, and with all the difficulties that are occurring over in that area, is that project moving forward?
Yeah, so, that as far as I know, I mean, that's more, I guess, maybe a question for the Ultrasat leadership, but as far as I know, nothing has changed.
Oh, okay. You are involved in that, though, yes? I thought you were. Oh, right.
Yeah, that's right.
Congratulations, too.
Yeah, thank you.
I have a question about we were talking about earlier about death signs
Yeah.
for supernova on the way, and And Beetlejuice, I'm sure you get this all the time. Beetlejuice has been in the news.
Yeah.
Have you seen any indication of Beetlejuice maybe being in those very late stages where it could be in the realm of a human lifetime?
Right, yes. So the analogy that I like to use for this is how difficult it is to do earthquake early warning. So I used to live in California, and there a whole thing is, can we predict when there's going to be an earthquake? And so the thing with earthquakes is that what you want to know is, when is the big one coming? And what is true is that when you have a giant earthquake, usually beforehand there were smaller ones.
Right.
And so people ask the question, oh, can we predict it? But the problem is, if you flip it around, just because you have some smaller ones doesn't mean there's about to be a big one.
Right.
And it's very similar for supernova early warning, which is that it's true that when there's a supernova and you go back, it was doing things before it exploded, but it is not clear that just because you do things, you're about to explode. So that's the difficulty. Betelgeuse is an older star, so it will explode at some point in, from what its perspective would be, the near future. But that doesn't mean that that'll happen from, in the near future for us.
Right. Maybe, are there any differences spectrally that you might look out for?
Spectrally, yeah, not that I can really think of.
But are you saying, like, can we tell if it's more larger elements? I think maybe that's what the other Mark is asking.
Right.
Yeah, I mean, the element changes are really happening pretty deep inside. So that
Right.
would be something you would see in a spectrum.
Gotcha.
In a spectrum, you're actually only seeing the very outermost parts of a star from its
Right.
spectrum.
Right.
Any other questions?
Oh, about the telescope that was modified at Palomar.
Yeah.
Was that originally a Schmidt camera and it was kind of changed to something else, to a detector type scenario?
Yeah, so it's a Schmidt telescope.
Right.
It was a photographic plate originally, I believe, at the on the focal plane, but then now, yes, now it's a big CCD camera.
Gotcha.
And I think the plan is to change it to a CMOS camera in the next decade or so.
Right. So it's probably a fast optical system like f2, f1.5,
Yeah,
f3.
yes, but I honestly don't remember the exact.
Okay.
Yeah.
Yeah.
Okay, any last questions here?
No, thank you. That was great, Anna.
Yeah,
Thank you so
that's
much.
wonderful. Yeah.
Yeah, it
It was
was.
really fun talking with you. Thank you so
Good.
much for all your questions. And like I mentioned, if you have any other questions, don't hesitate to reach out.
Thank you.
Thank you very
Thank you,
much.
Ann.
Yes, thank you.
Nice to meet you.
Thank you very much.
Take
Great
care.
job.
Thanks.
For those of you who have joined us, just want to mention that we have a public telescope night actually coming up this week. Is our February event. Unfortunately, the weather doesn't look too good, so stay tuned for that. If it is cloudy, the next one would be March 21st, Thursday, March 21st. And so maybe you could join us then. But the next meeting will be Tuesday, March 13th. And we are going to have a presentation about the upcoming eclipse. And so hope that you can join us at that point.